All right, gang, let's wrap this unit up with compound interest. By the way, that link up there is to an article that my dad sent me a long time ago. The title is "The One Word I'd Like to Tell My Younger Self." It's from the Wall Street Journal. And spoiler alert, the one word is compounding. So, very important lesson for your understanding of just investing and the importance of starting early. You need to start the minute you finish college or get your first real job or get out of the military, whatever you do when you start investing right away. Contact me to talk more. All right, let's see. Compound interest. Interest added on to a principal. Okay, the percent rate is typically given on a yearly basis, but could be applied more than once a year. This is known as the compounding frequency, how often it's compounded. Let's take a look at a typical problem to understand how compounding frequency changes how interest is applied. So we are going to invest 500 bucks in an account that earns yearly interest rate of 4%. So the question is, how much would this investment be worth in 10 years if the compounding frequency was once per year? Okay. So we have 500 bucks. And we're still going to have that 500 bucks plus another 4%. So we use 1.04 at the end of year one. All right, but then we'll take that amount and multiply that by 1.04, and that'll tell us the amount after year two. And then again times 1.04 to know how much is in the account after year three. And so on until we do that 10 times, and that'll tell us how much is in the account after 10 years. So why repeat ourselves? Let's just use exponents, repeated multiplication, and we're going to get approximately $740.12 in the account 10 years from now. That's the power of compounding. But what if we compound 4 times a year? Okay, this is called quarterly compounding. There's 4 quarters in a year. The question though is, why would it not make sense to multiply by 1.04 each quarter? That's because we're getting 4% yearly. 4% here is a yearly interest rate, also known as an APR, which stands for annual percentage rate. So what would we do? It would be 1% a quarter. Why? 4% divided by 4 quarters is 1% per quarter. So to calculate how much is in this account now, if it's being compounded quarterly, now this, gonna need a little more room here, would look like this: 500 bucks times 1.01, excuse me, for year one, quarter one, then times 1.01 again at the end of year one, quarter two, and then for quarter three, and for the end of year one, quarter four, and then we get finally into year two, quarter one. Now we got to do that repeatedly until we get to year 10, quarter four. I don't want to do that, so I'm just going to use my brain and think, okay, how many times am I actually multiplying by 1.01? 4 times a year for 10 years, that's 40 years. And this evaluates to $744.43. And this is what you're going to find is that generally, if you take the same rate and you can break it up and have it compound more often, you're just getting a bigger amount quicker so that you can build faster and build higher. So it's generally a better move. All right, turning the page. This pattern is fairly straightforward. You should recognize the structure here. The only difference is that now it's adjusted modified for compounding. So we have to divide, just like we did on the previous page where we divided the 4% by 4 quarters and then multiplied by 4 in the exponent because we're just compounding more often, so we're multiplying more often. So if I were to redo that previous example, just to bring it in here, not redo it, but bring it in here to take a look at it, how it compares to this formula. We have our principal, 1 plus our rate, divided by number of times it's compounded, to the number of times compounded times time in years in that case, power. And that's what's going on here and here. All right, so now let's take a look at that. The rate in the previous formula is referred to as nominal, as in name only. It's known as this because you effectively earn more than this rate if the compounding period is more than once per year. Based on this, bankers often refer to the effective rate, or the rate you would receive if you compounded just once a year. So let's take a look at this. An investment with a nominal rate of 5% is compounded with different frequencies. Given the effective rate accurately to 2 decimal places for each of the following, give the effective rate accurate to 2 decimal places for each of the following compounded frequencies. Show your calculation. So here we go. All I got to do is take basically the parentheses and exponent part of the formula because we don't know the principal. So I'm going to take 1 plus, and in this case, the rate is 5%, compounded quarterly, 4 quarters in a year, and raise that to the 4 power. Again, we don't have a time frame, so we can't really multiply that. But anyways, I did that ahead of time on Desmos, and I'll show you what that looks like here. Where did I already embed that here? Yeah, you'll see that starting on line 3, 4, and 5 there. And so what do we got? We got approximately 1.0509, which, as you know, in percent form is 105.09%, which means we got approximately a 5.09 effective, and I like to put the word actual the first time, actual growth rate or annual growth rate. And then monthly here, same idea, but 12 months in a year. And this one comes out to approximately a 5.11% effective yearly rate. And then lastly, daily. 365 days in a year, roughly. If we want to get into it, closer to 365 and a quarter, hence leap years. But this gets us approximately a 5.13% effective yearly rate. So again, the more times you can compound, the better. Moving on to example 69. Okay, what do we got? $1,000, nominal 2% yearly rate, compounded monthly. We're just plugging all this into the formula. So we've got $1,000. Our rate is 2%. Compounded monthly, 12 months in a year, to the 12 months times 20 years. In other words, it's going to be compounded 240 times. And punch that in as well. That's in that Desmos file that you can take a look at if you like to see exactly how I typed that in, but it should look pretty similar at this point. I got choice 2. Moving on. Last page of notes for the unit people. Okay, so we could compound at smaller frequencies. Intervals eventually compounding all moments of time. In other words, we'd be letting n in that formula approach infinity. Interestingly enough, this gives rise to continuous compounding and the use of the natural base E in the famous continuous compound interest formula. So it's literally just, we say for short PERT, A equals P E to the RT, and you basically just plug in again, but this formula will do the same job just a little more efficiently. And if you want to get into it, I have a great series on how that formula does actually equal the previous formula, but it's just nice to know that it's just a little more concise. So that would be our formula. We just literally plug everything in, a 2% rate, investment of 350 bucks, and then let's use it. Let's evaluate it. How much after 20 years? Plug in 20 for a time. And I evaluated this as well. There it is on line 7, 522 bucks roughly. And then lastly, now again, algebraically means we're going to have to use inverse operations. We could use a calculator to guess and check to make sure we're right, but we want to determine the time it would take the investment to reach 400 bucks. In other words, at what time will this formula get us 400 as an output? So again, guess and check would mean just try different values of t. Now we could guess less than 20 years because we're over 400 already at year 20, and we just play around with it till we get it. But algebraically, we're just going to isolate that exponential and then use logs, and in this case, the natural log, to invert the exponential part. So we got e to the 0.02t equals. And again, I like to leave these in fraction form just because it's more exact, but it's up to you. You could get a decimal value for that and work with that moving forward. Now, this would get us a log base e. I'm going to bring down your base, perform the old switcheroo on your exponential to your log, and we have log base e of 400 over 350 equals 0.02t. Now, you could get a decimal value for this here, right? And then divide it by 0.02 to get t. I'd just much rather be efficient, come up with a formula, and while I'm at it, I'm going to substitute in for log base e, just the prefix or the abbreviation natural log. So we're going to have the natural log of 400 over 350 divided by 0.02. That'll get us t. Again, went ahead and calculated that. That's our last line there. That's line 8. And you can see it's somewhere between year 6 and year 7, closer to year 7. So we're going to say about 6.7 years. And that, ladies and gentlemen, is continuous exponential growth. Miss you guys. Hope all is well. Hang in there. Keep in touch. Let me know if you need help with anything. Over and out.